There's a...
Every single student state. Ready? Hi, and welcome to the second Lytle lecture of our Lytle lectureship this year, and as well as the EE Colloquium. We are very excited to welcome Professor Stephen Boyd from Stanford as our Lytle lecturer this year. And I think Stephen really does not need any introduction. I know a lot of you are already familiar with a lot of his work, coursework on convex optimization, the convex optimization textbook, joined with Lieven Vandenberg, a lot of lecture material, videos that are online, and they're super popular. I think that his webpage has 1.6 million hits every year. Also, open source software and codes available, CVX, which is a parcel solver for convex optimization. If you haven't been to his website, I really encourage you to go there. Lots of things to watch. And it's no wonder that his classes at Stanford have more than 200 students. So this audience is actually small for Stephen. I also wanted to just briefly mention I'm personally very pleased, as I had the very good fortune to be a PhD student of Stephen's at Stanford. And the first time I heard him lecture was in a course that I took my very first few weeks at Stanford as a graduate student with another instructor. But Stephen gave a guest lecture in that class where I really felt, was I in the right class? Because the material suddenly seemed so much more clear and much more interesting. So I dropped that course. Then I took it later when Stephen offered it. And since then, I took all his courses. And that was a great experience. So I hope you all enjoyed the talk. And welcome to Stephen.
Thank you. Thanks, George. Right. So, just to make sure, this is the one with equations. All right. Well, it would be awkward anyway. You can't get up and leave now, unless you're sitting at the back. So, this is going to be, it's an overview lecture. So it's not going to go into any, detail or whatever, but it's supposed to just give you a flavor for, what is convex optimization? Why should you care about it? And then also we're going to look at two sort of recent things my group and other people have been working on at two extremes. One is solving small problems very quickly, and the other is solving just gigantic problems, right? So it's just a big survey. We'll just do a little bit of each of these things, but you should come away with the idea of what this is. Okay. So I'll start by talking about convex optimization. Then, and this will just be sort of a broad overview, maybe 15, 20 minutes, something like that. If you actually know anything about it, you'll be bored or something like that. But it'll just be an overview. And then I'll talk about real-time embedded optimization, and then large-scale distributed optimization, and then wrap up. So we'll just sort of see overview. We'll look at two more specialized topics a little bit more closely, and then wrap up. OK, so convex optimization. So here's the classical form. This is what a convex optimization problem is. You have a variable, x, that you need to choose, and you have an objective, f0 of x, and you're supposed to minimize this, subject to a bunch of inequality constraints and equality constraints. The equality constraints have to be linear for this problem to be convex. That's required. The inequality constraints and the objective have to have non-negative curvature. So basically, the functions, the graph has to curve up, right? I mean, it can have no curvature, in which case these are linear affine functions, right? But they can't have negative curvature. So this is the idea. So that's a convex optimization problem. That's the classical form. Now, the modern form actually makes it look closer to linear programming. And that looks like this. You minimize a linear function subject to the equality constraints. That's no different. But all of the nonlinear constraints are stuck into a cone. It says that this variable x has to be in some cone here. And by different choices of cone, this is different problems. If this cone is basically the non-negative orthant, that's a set of all vectors with non-negative entries, then this is linear programming, right? So it's an old problem family. If it's a Lorentz cone, so it involves like a 2-norm or something like that, it's what's called a second-order cone program. And if this is the cone of positive semi-definite matrices, this is called the semi-definite program. And I'm not going to go into the details, but these are much newer things. Semi-definite programming is maybe something like I don't know, 15, 20 years old. Or I mean, like many things, it traces way back if you look. But, you know, its popularization occurred maybe 15 years ago, something like that. Okay, so this is sort of the modern canonical form. And by the way, later I'm going to explain why most of you don't need to know about this. So that's coming up later. Okay, so that's the good news. Okay, so why would you study convex optimization? Well, the first reason is these are going to be in inverse order of importance. That's to me. So this is completely subjective. This is just my feeling about it. So the first is there's a beautiful and nearly complete theory. I mean, it's just beautiful. You have this idea of duality, and you get these optimality conditions that are necessary and sufficient. It's clean, it's pretty, it's beautiful. It's an aesthetic thing. Now, the second, another reason, I mean, very important, is this. There are effective algorithms and methods for solving these problems. Okay, now that's actually very important. By the way, that's both in theory and in practice, right? So in theory, it means there's multiple theories under which basically say if this is your computation model and your complexity model, we can solve these problems. I mean, roughly, they say that. And in practice, it's also true that these problems can be solved very effectively. Now, what's nice is, by the way, solved means the strongest form of solve you could possibly mean, right? It doesn't mean, you know, usually if you do optimization, someone says, oh, yeah, I minimized this, and they didn't, right? Because what they really did was they found a local minimum or something like that, you know? And it may be good enough for what you are doing, but that's not solving it. Here, this means the global solution. Oh, and by the way, you don't just get the global solution, you get a certificate proving that it's the global solution. So you don't even have to trust anybody, right? You simply say, here's the solution. Oh, and by the way, here's a certificate proving nobody could do better than this, right? So it's very nice and complete. Okay, and I mean, if you care about these things have polynomial complexity, although don't look too closely because there's some weird hidden constants in there that, anyway. Okay. Now, another reason to know about it is actually, I mean, it allows for conceptual unification of a lot of methods, right? So if you take machine learning, for example, right, then, you know, you learn about regression and then lasso method, and then you look at classifiers and this and that, and, you know, logistic regression and SVM. And what's very nice is just to step back at some point and say, these are all just convex problems. Now, maybe that doesn't help because you have special methods for all these things, but it's just an interesting way to get conceptual unification of all these things. But this is the main one, at least for me. I mean, I think the real reason to study it, I mean, all of these are coupled, right? There wouldn't be tons of applications if you couldn't actually do it. We can start with that, right? So these are coupled, they're not independent. But the main thing is there's just tons of applications of this. I mean, that's the interest for me. So the application areas would be things like, well, machine learning and statistics. We'll even look at some examples, finance, supply chain, revenue management, advertising, control, tons of problems. Signal and image processing, vision, networking, both design of a network, operation of a network, even circuit design, combinatorial optimization. That's strange because that doesn't sound like convex optimization, but they're very tightly coupled, and there's a very important role for convex optimization there. And there's all sorts of other bizarre areas like even in quantum mechanics now. For example, quantum information, stuff like that. These are things I don't know about, but apparently these are application areas. All right, so let's dig a little bit more deeply. Let's look at machine learning, right? Or statistics, whatever you want to call it. Or AI, I guess that's the other name for it. Those are politically charged names, of course, right? So depending on where you are, you use the wrong term, you could be in big trouble. So you want to estimate parameters, right? Say for regression or classification. And these are almost generically convex problems. Well, many of them. The general form is this. If you're doing either maximum likelihood or map estimation for any exponential family, that's just a convex problem. I mean, there's some things that are being hidden in there, but roughly, that's actually technically true. And this would include things like the oldest convex optimization problem that there is in the world. That would be least squares. By the way, also the one that is still the most useful and the most widely used, least squares. Okay? But you know, modern forms of that would be lasso regression. That's where you take least squares, and to that you add an L1 regularization. We're going to talk about that. And things like classifiers, logistics, support vector machine, but lots of other things, multi-way classifiers and things like that. Now, another interesting thing that we're going to talk about is once you start getting into sort of modern convex optimization, what happens is things that were important in traditional optimization are no longer important. Here's an example, gradients, differentiability. So you take a course, a traditional course on optimization goes like this. We're going to do optimization. You come in, we'll look at the gradient method, and it makes sense. You kind of step in the direction where the function's getting small the fastest, and then you do Newton methods and quasi-Newton, and it goes on and on, conjugate gradients. And anyway, but throughout that class, the assumption is, of course, that you have gradients. So smoothness looms very big. If you take the traditional course on optimization, smoothness is very important. Turns out in convex optimization, it's totally irrelevant. Just doesn't matter. And in fact, the most interesting problems you solve are not smooth. We're going to see lots of examples of this, okay? So one very good family of examples is you take L1 regularization and you add this to a problem. We're going to talk about this in more detail. And what happens is you get solutions that are sparse. And we'll look at this. We'll look at applications of it and stuff like that. This has been used for a lot, more recently in things like compressed sensing. But it goes even back to the 90s, and actually in geophysics it goes back to the 70s, I think. People were using total variation reconstruction. Now, there's a ton of problems, of course, that are not convex. I mean, it's, but a whole lot of those are actually biconvex. So there's two sets of variables, and if you hold one fixed, you can optimize its convex in the other, and vice versa. And this would include a whole lot of things like k-means, EM, actually autoencoders. These are all biconvex. So, okay. So let's look at a specific example, support vector machine. So what it is this, again, for people who don't know about this, you're given a bunch of pairs of a vector, that's a feature vector, so some big long vector that has things that may or may not be relevant. If you're doing spam filtering, this could be word counts or things like that. A lot of them could be Boolean. They're either 0 or 1. It's presence of an attribute or not. Okay, something like that. And then you have an outcome. That's BI, and we'll just call it two classes, so it's -1 and 1. Okay, so that's your data. And then what you're going to do is you want to make a prediction that is going to be the sign of an affine function of the feature vector. So that's W transpose A minus V, and you take the sign of it. Your job is to choose W and V, right, to prox. If you've given you some data, actually what you really care about is how you do on future data, not how you do on the data you've seen. Okay, so support vector machine, that's which is just used everywhere, says this. It says that you should choose these using the following rule. You should minimize this thing, that's the average loss, and this is easy to pick apart. What you want is you want this to be positive when this is positive, and you want this to be negative when you want this to be negative. So what you really want is you want this expression here to be positive, right? And what this says is if this is over the value 1, you don't get charged at all. That's what this expression says. Okay, but you start getting charged if you get below 1. So that's it. And this is the average loss. It's the loss over all the examples you've seen. Now, you want to achieve this with a small w, and that's this regularization you add here. So if you've seen this, great. If you haven't, well, you should, basically. Everyone should see this. And the picture would be something like this. So here we're doing, this is classification with two features. Now, of course, you don't use heavy technology to do two-feature classification. The way you do two-feature classifications is you use your eyeball, right? You look at the scatter graph. If they're all intermingled together, you just turn around and go home, right? I mean, and if they're roughly separated, you draw a curve. You take a hand and you draw a curve through it, and you go, that's my classifier. Okay, but so I mean, don't take this seriously. The point is this is used in dimensions like 10,000, 20,000, a million, okay? Where the ability to hand draw a separator is not open, right? And so this would be the idea. And here you can see that the two classes are not completely separated. Here's some on the wrong side. Here's a couple on the wrong side. And so this is what you'd end up with. Okay. So, and I should say, for those of you who don't know, this is used very widely, all around, everywhere. Many areas, many application areas. Okay. So I want to talk now a little bit about, something you can do. This is something you could do with sort of modern convex optimization, and it's really, it's very interesting. Here it is. It's a very simple idea. It says if you add a positive multiple of the sum of the absolute values to the objective and minimize, what happens is you tend to get an x that's sparse. But not just approximately sparse. It's not like, oh, some of the entries are small. A whole bunch of the entries will actually be 0, exactly 0. Okay? So that's sort of the idea. And this parameter lambda controls how much sparsity you get. Of course, every time you do that, you pay in the other objective. Okay, so that's the idea. Now, what this does is it preserves convexity and therefore tractability. But notice that why this would not have been done in 1930 is that this is not differentiable. It's not. I mean, obviously, absolute value's got a point at the bottom, right? And you can imagine all sorts of arguments. They're incorrect, but here would be one. You'd say, like, it's absolute value. It's differentiable almost everywhere, right? It's differentiable everywhere except at 0. Then you say, look, only a mathematician would worry about something that has a derivative everywhere except at one silly point. Okay, but the whole idea here is that very often x is 0, which is exactly that at that point, right? And the other thing is if you start minimizing things with sharp corners, of course a lot of times you end up right at those points. Okay. I was going to say that's the point, but I shouldn't. So okay, all right. So all right. So all right. So this has been used for many years in many fields. In sparse engineering design, you do this. Feature selection in machine learning, you can do this with it. It's amazing. I'll describe some examples of that a bit later. Total variation reconstruction and signal processing, and compressed sensing would be examples. And we'll look at some. So here's a very famous example right now, which is lasso. It's very cool because it goes back to least squares. Least squares is like from Gauss. Like in 1803, he wrote a book on this in Latin, about least squares. I mean, so this is not a new thing, right? Least squares has been used for a long time. And then you add, so this is from 1803, probably earlier or something. And then to that you add this L1 term. And basically that takes you right to the present, right, to the modern era. Now what's cool about this is, that's the normal regression term. And then this is something that promotes sparsity in X, which, by the way, has a beautiful interpretation. This says, please approximate my data as a linear combination of the columns of A, which are like features. So you're saying, please predict, tomorrow's, euro, overnight rate as a function of these 500 other things. That's what you're asking, right? I mean, we'll see how good a job you can do, but that's the idea. And if X is sparse, what it says, it's really cool. If X has only 10 non-zeros, what it says is, I can actually predict that pretty well using the following 10 things, right? And then you list off these 10 features. That alone is interesting. Well, I'll mention some other examples a bit later. Okay, now here, the other thing I should mention is something very cool here. So when X is sparse, you've done feature selection. Now if you go back, and I'm going to grossly oversimplify, but here's statistics before this. It goes like this. You walk up to someone and you say, I want to predict these things based as a linear combination of these things. This is regression. But the point is, they say, sure, how much data do you have and how many parameters in your model? So normal rule, this would be reasonable. You'd say, well, I have 1,000 data examples, and I have 20 parameters in my model. That's reasonable, right? Because, it's something like it's a 20-to-1 reduction. Everybody got this roughly? By the way, if someone said the other way around, you would turn around and walk away from them. Because it makes no sense, right? It's like it's hideously overfit, right? If I say, yes, I'd like to fit this model with 30,000 parameters, and I have 400 data points, it's ridiculous, right? Okay. However, here it's widely done. It's unbelievable. It's really cool. And the way it works is this. And here's a very common one. It's a gene expression experiment. It goes like this. The X here, genes. So you got tens of thousands of these. It's gene expression, right? And then you're trying to predict some medically relevant quantity. That's all lined up in B here. Each row is a patient. And so you have a couple hundred patients, let's say. And so there you are. You're saying, what are you doing? You say, I'm fitting a statistical model. How many parameters in your model? 30,000. How much data do you have? on which to fit this model, and you'd say, oh, 350, right? It's just totally backwards and wrong in old statistics. This is just fine, because what will happen is no matter what value of lambda you pick, you'll never choose more than 350 parameters, and it's really interesting when you crank lambda up and you start picking like, 27 non-zeros, right? And in fact, a lot of times, what's most interesting is actually the 27 you picked, not even the model, right? And so I have friends who do this. They're biologists, and they would look at these things, and I was horrified to find out they're doing this. And I said, you don't believe any of it? And they said, oh, no, of course not. So they said, no, it's very simple. They look at the list of 27 genes, and they go, yeah, they look at the first 10. They go, yeah, these are like duh. Of course that's related to that. And then they look at the next 5, and they go, I could have guessed that. They look at the next one, and they go, no, that's totally wrong. I don't know where that came from, right? And then they look at the next 3, and they go, that's very interesting. That could be. And then they make a quick phone call to their postdocs who stay up all night. And the next morning, it's known whether those other ones were, it actually may be longer the next morning. But anyway, that's how it works. Okay, everybody got that? Okay, so now if you compare this to, this is from the 30s. In the 30s, what you do is you'd say, look, there's not much difference. You're adding the sum of the squares. This is some of the absolute values. This is ridge regression, right? So this is very common. And by the way, you do this because this has an analytical formula for the solution. There's no analytical formula for the solution here. Okay, so that's the idea. But here's what's weird. If we were to bring Fisher back and say, Fisher were to ask, what are you doing now? We'd explain. I wouldn't. I'd actually have my stat colleagues do. I'd be afraid to do. Anyway, so I'd have my stat colleagues explain, well, we do this now. And they'd look at it for a while and say why, and we'd talk about sparsity and all sorts of stuff. And then finally he'd say, but that's not smooth. And we'd say, yeah, but what would you do if we told you we can solve that in the exact same amount of time it takes us to solve that? Not exact, but roughly, right? And that's good enough. That's not obvious, right? So okay, so let's look at an example. Here's lasso. So what we're doing here is it's one of these reversed situations where basically here's some true x. You can't see it, but that's 1,000 things. Only 200 are non-zero. That's these little spikes you see here. And then I'm going to give you 200 noisy measurements of 1,000 things. Okay? It's completely ridiculous. It's like somebody walking up to you on the street and saying, oh, I'm thinking of the sum of I'm thinking of 5 numbers. They add up to 32. What are they? And you're like, well, the answer is, I don't know. There's lots of answers to that, right? It's totally ill-formed. But here you're going to take the prior that these things are sparse. Now, by the way, once you knew if I told you which 30 were non-zero, we're back in old comfortable statistics, because then I'd say, please estimate 30 parameters. I'm giving you 200 measurements. Everything's happy. You do regression, and you get some beautiful smoothing and blending of the measurements and blah, blah, blah. Okay. So not surprisingly, it's ridiculous, right? You have undersampled 1 to 5, and that's what comes out. It's complete nonsense. Okay. Here's the lasso reconstruction. It's spooky. If you have seen these things, then maybe you're used to it. By the way, even if you're used to it, it's very good to get the wonder back. This is ridiculous. It's implausible, but it's true. This happens. If you haven't seen this, you should be. If you are not shocked and haven't seen this before, you should be shocked, or you're not thinking about it deeply enough. This is just like weird, right? To make 200 measurements and then to predict 1,000. Now there's a prior, of course, that it's sparse, but this is the idea. By the way, these things degrade drastically. They go from working shockingly well to then total collapse and uselessness as they pass some, boundaries in parameter space. But this is the idea. Okay. So let's talk about how do you solve these problems. Well, for medium-scale problems, that might be thousands of variables up to 10,000s of variables and constraints. People do this by interior point methods on a single machine. That's pretty standard. And so this is almost technology now. I mean, we can just do it. Just works, right? And here, it's key to exploit the sparsity. And it's not quite a technology, but it's getting there. It's getting there. It's getting. Parts of these are actually technology. Right? By the way, I'm using technology here in a sense where it's actually the highest praise, because what I mean by it By the way, people who work on these methods then get extremely angry and they start yelling at me and stuff like that. But actually, it's the highest praise. What it says is the theory is known completely, much is known about it. There are algorithms have been developed, and much is known about them. You can prove things. I mean, also you have known complexity. You know how everything, what the sensitivities are. And then you have excellent, correct implementations of them, to the point where the rest of us can just use them. Most of us can just use them, right? Actually, what happens is when they do yell at me, I'll say things like, do you use TCP/IP? Well, of course they do. You can't turn around without, using TCP/IP somehow, right? It's how all things talk to each other. And I'd say, do you know how it works? And of course, most people who work on interwar methods, they don't know how it works. And I'd say, well, there, you see? That's not trivial, right? That's something where a lot of thought went into developing those algorithms, establishing correctness, and then you have to have a correct implementation. And the result is that the rest of us can consider this as just something like a certain bit pipe, right? So that's technology. It's the highest praise. So anyway, just to make it clear. Okay. So what has come along, again, something that's got an old idea, but something that's relatively recent, meaning in the last 5-7 years, is the idea of modeling languages for convex optimization. The idea is you describe a problem in a high-level language, and then you automatically transform that to a standard problem, and then you solve it, right? So this is the idea, right? So, the idea of a modeling language goes way back. A modeling language that knows a lot about convex optimization, though, is not. That's something relatively new. And what this does, it enables rapid prototyping of problems, for small and medium problems, and it's great for teaching. Right? Because when I taught this course before these things and after. And before, it's mostly a math class. You ask them to prove something, show this, and everything. Every now and then you have a numerical problem, but you have to be very careful so that it's such a huge pain in the ass to code it up. But with these things, what you can do in a 15-line script is stunning. So what happens now is you teach a class like this. You will, if you take that class, you will do finance, you will do portfolio optimization, you will do signal processing, you will do control, you will do machine learning, you'll do all. And maybe, these are baby problems, but you'll do them. And it actually changes a lot. It's fun. Okay. Here's an example of one of these things. There's many of them now, but one is maybe the most widely used is CVX. And that's something written by Michael Grant, maybe about 8 years now or something like that. And so here's the mathematical problem. That's a support vector machine. And this would be the source code you'd write to express that problem. And the point is, it's written on top of MATLAB, which is something I don't want to talk about. But anyway, it is. And so there it is. But the point is, that the source code here looks like really close to the math. And that's what you want, right? So that's it. Now, by the way, this would be slow compared to whatever some state-of-the-art, SVM package would be right now. But what's kind of cool about it is you can imagine that suppose I told you that for some reason I wanted to insist that the first 10 entries of W were positive, right? Just because, I don't know, that's my problem, right? Then it would actually be very easy to put that in here, right? Immediately, you just declare it. So it's like a declarative language, right? You say what you want, and then you let this thing figure out how to get it. So that's the idea. Okay. That's the overview. Now what we're going to do is look at these two extremes, these two extreme examples. And the first one, the first example is going to be, the first thing we're going to look at is in real-time embedded optimization. So the idea is this, that in a lot of applications, some of the ones I talked about yesterday, what happens is you're going to solve the same problem repeatedly with different data. So that's an example. And in control, that's obvious. In control, you're planning out, let's say, 3 or 4 seconds of flight, and you're going to choose, 40 sets of control surface configurations, 40 steps out, maybe a few seconds or whatever it is, right? And then you're going to do this every 10th of a second. So every 10th of a second, you're going to resolve a problem. It's the same problem, but with different data each time. If you do finance, you have the same portfolio problem, but the problem data will change each time, right? Your current portfolio changes, right? Because things either went up or went down or whatever, or you bought stuff. And other things like predictions of returns, predictions of transaction costs, they change. So you'd put those in. Now, of course, this is used now. when solve times are measured in minutes, hours, right? So for example, supply chain stuff works this way, right? Or scheduling, right? So airlines solve some optimization problem once, and then they have some contingencies. They rerun this, but it's kind of like we're talking on an hourly basis or something like that. Supply chain stuff might be done on an hour, 24 hours, this kind of stuff. Chemical process control is done at like 15-minute time scales. Okay? So, by the way, this sort of fits with the old picture of optimization. The old picture, locked into place in the 1962 or something like that, is you should visualize some old Cray computer, a bunch of people sitting around it with white coats, who are taking care of it or something. It's a big iron thing, right? That's, so who could afford it? Well, if you were going to design a nuclear weapon, you could afford it. If you were Goldman Sachs, you could have one in a basement somewhere, right? But you're supposed to think of it as high value, big iron stuff, okay? So, and therefore things would take minutes, right? Seconds, at least seconds, but probably minutes, to schedule generators for California or something. That might take an hour or so. I mean, these are big. And by the way, this is kind of, if you do this kind of, if you make optimization, this is how you're cool. So you go to the conference and you say, I just solved one that was this big, and it took 10 minutes, and people go, wow, that's cool. Okay, so that's the idea. Okay. But what happens is no one talks about solving them fast. And in fact, people assume you cannot solve them at millisecond timescales or anything like. In fact, I'll tell you in a minute. So it turns out, new techniques, you can actually solve optimization problems in timescales measured in milliseconds or microseconds, right? So, by the way, this is something not many people know and is completely unappreciated. I don't even think anyone has any idea what the implications are, right? So I'm in control. I was in control, or maybe I still am, I don't know. I may be still in control in the field. But the whole idea of control is someone says, what do you do? And you say, well, I make decisions on, so I make decisions, but I make them 50 times a second. And they go, well, what kind of calculations do you do? The answer is you multiply by a matrix. That's what you do, right? So that's like I do 27 multiplies, right? And they say, can't you do more than that? And you go, no, I do it every 10 milliseconds. I can't have a complicated. Well, you in finance, you're rebalancing every hour. Of course, you have the luxury of solving some gigantic problem. You see what I'm saying? It turns out that's all wrong. Even if milliseconds, you can solve an optimization problem. I mean, no, I don't think anyone gets. I have the feeling this is good. This has implications for a lot of things. If you're in a field, by the way, where you make decisions in, on the order of milliseconds or something like that, and you've been using simple methods because you don't think you can do much more, watch out, because I think this might be coming to your field, right? So, actually, better yet, you could import it into your field. Anyway, so, okay. Let's look at an example. So it's from control. So we have a disk head. Actually, it's just a positioning system. I'm going to move something from here to here as fast as possible. Okay. I'm going to put a big force on it. I'm going to put a force on it here, and I'm going to push it really hard because I want it to go fast. Okay. Now, because I'm going to put such big forces on it that I can't. It's not just a rigid body. So I'm going to write it as 2 vibration modes. So it's really like 3 masses connected with some stiffness and springs. Okay. And the idea is you want to find the force here that moves this from one place to another as fast as you can. Well, that's a quasi-convex optimization. It's a convex optimization problem, basically. Okay? Oh, by the way, this is one where you'd find all sorts of classical control literature on this. And, the Hamiltonian would come out, and all sorts of things would come out, Pontryagin, maximum principle. Useless. It'll work for like 1 mass, maybe 2. That's it, right? Modern view is it's just a convex problem. Okay? So here's an example. Is for this one, here's the minimum. This is the force you should apply right there. Okay, that's it. Okay. Now the point is, look, if there were no vibration modes, and I ask you to move a 1 kilogram weight from here to the answer is really simple. You accelerate, you push as hard as you can, right, until exactly the midpoint, and then you go to maximum braking. Some people drive like this, right? So you you know what I'm saying, right? Oh, by the way, the name for that is bang bang control. Just so you know. Okay. So, all right, fine. So the point is, and then look, if you're going to move a mass from here to here, obviously you have to push it to accelerate it in the right direction, and then later you have to brake it. So we do see some pushing. That's pushing, and that's braking. That's braking. That's braking. Okay. Here's what's not obvious. I mean, there's no way you can look at that and say, oh, I was going to try that, actually. I mean, there is no way, right? So, by the way, this is a baby example with 3 masses, 1 actuator. The point is, now imagine the same thing with a 50-state linear dynamic system with 6 inputs or something like that and all sorts of complicated constraints. Real simple. People are out, right? Okay. Now, the question is, how long does it take to compute this, right? And the old answer would have been a second or something like that. And then you'd say, gee, thank you for telling me the optimal thing to do with my disk drive. It takes a second to calculate that the optimal trajectory takes 7 milliseconds. So you can see the issue here, right? So anyway, but it changes, right? So I'll talk about that later. Okay, so what do you need in a solver, in an embedded solver, right? So the idea is you need high speed. So you may have to do this in every 10 milliseconds, every 5 milliseconds, something like that. You need extreme reliability and robustness, right? So you can't have floating point exceptions, and you have to be able to handle poor quality data, okay? And you need a small footprint, right? You couldn't have stuff like that that does memory allocation or garbage collection, right? So trust me, you do not want to be in a vehicle when the primary control system starts doing the garbage collection. I mean, this is not a good thing, right? So this is just out of the question, right? So, these are the kinds of things that you need. Okay, so how should you do this? Well, first of all, if your problem takes 15 minutes, if you have to make a decision every 15 minutes, use whatever you want, right? By the way, if every now and then you have an exception or some problem, try it again. Perturb the data a little bit and try it again. Maybe it'll work, right? You have enough time. Otherwise, you develop custom code. You can either do that by hand or automatically via code generation. I guess in my group we did a couple of these, and then moved to code generation. Now, when you generate a specific solver for a family, you can exploit all sorts of stuff, like, sparsity patterns, all sorts of stuff. You can do a lot of stuff ahead of time. And what happens is bizarre. You get I would have imagined a speed up of 10 to 1. That's easily understood. But in fact, the typical speed up is like 1,000x. Okay? So, by the way, if you want to allocate that 1,000x across people who get the credit, you know who mostly gets the credit? Compiler people. What was the suggestion? Sorry, okay. So I would say most of that credit, by the way, goes to compiler people, people who do optimized backends that do the code optimization. I mean, that's really it. We'll take a little bit but mostly this goes to the people who do that. Still, either way, it's just fine. It's actually stunning, and this changes a lot of things. So let me just sort of make this clear. I mean, this is kind of obvious, right? Something like CVX is a parser solver. You take a problem instance, transform it to a new problem, and you get a solution. Whereas a code generator would look like this. You describe a problem family that generates source code. You compile that source code, and now you have an ultra-fast solver that maps problem instances into solutions, right? So that's the picture. And here, there's actually multiple ones now, but there was one a student of mine a couple of years ago worked on, which is CVXGEN. And it's just a proof of concept thing, but it actually works. So it handles little small problems, maybe with a couple hundred variables, maybe 1,000, something like that. And what happens is it looks at the problem family, and then what comes out is completely flat, actually library-free C. Doesn't even use the math library, unless you turn on, and if you turn on verbose, then it needs a square root. Otherwise, it needs nothing, absolutely nothing, right? So it's very small footprint stuff. You could embed this in anything. And in fact, we do things like run these on little ARMs and things like that and embedded things. So here would be an example. It's a baby SVM. I have no idea why you'd solve one this small, but if you wanted to, this is what it would look like. So here, it starts looking familiar, right? No, but this is all written in Ruby. So, I mean, the parser and the code generator. So what would happen is you declare the dimensions. These are parameters. In CVX, they have to be numerical. They have to be instantiated. These are parameters, meaning they're not instantiated until you solve, till solve time. Then you describe the problem, and it looks, just like what you think it looks like. Okay? And this is parsed, and then it's generated. Then you generate an intermediate form, which is actually a QP, and then you do some optimizations on that, and then you emit C source to solve that. Actually, these numbers are a bit behind, but the spirit is the same. Actually, just divide all the numbers by 5 or 6, and you get what it is now. Oh, and increment the processor family a bit. But anyway, so this would be like that little SVM problem. That would be a problem with, we'll look at the disk problem. That might be one with 600 variables, and it takes about 2 seconds to solve with some standard interior point solver. By the way, that's a multi-threaded that's a multi-threaded solver. This is just a single thread thing, and that's actually, I think the last I checked, this was at 500 microseconds or something like that. Okay, so this would be and you could make that shorter if you wanted to, but yeah. But so I gave a talk to a whole bunch of people in optimization. I talked only about this topic, about embedded solvers and things like that. And somebody came up to me afterwards. He said, "That was a great talk." And he said, "Remind me again, what's a microsecond?" So, yeah, I mean, come on, you can't blame. This is someone in operations research. What do they know about microseconds, right? They don't. This is not. Yeah. So I just want to point out it's weird to be talking about solving an optimization problem and microseconds in the same, in the same sentence. This is weird. Okay. So, okay. Now we're going to move to the exact opposite end. That was solving small problems repeatedly in real time. Now we're going to move to the other end, which is solving gigantic problems, right? And so here, I'll give an equally shallow description of this, but you get the idea. It's large-scale distributed optimization. So the idea is you want to solve just absolutely gigantic problems, right? So, I mean, one no-brainer is this comes up in, so-called big data, right? I can't say that, sorry. It's too, yeah, anyway. So, yeah, if you have, so that's one. But, it comes up in lots of other things. I mean, you can use dynamic optimization on large-scale networks will do the trick. So there you have like a power network, and you have a whole bunch of devices. Each one is dynamic optimization. So you're actually working out the power as a function of time for each of these, right? So, the next thing you connect these all up in some grid, and you put limits on the transmission lines. Next thing you know, you got a serious optimization. You got one with a lot of variables there. Okay, so now what you would love. Here's the fantasy. This doesn't exist, but maybe it will in a couple of years. I hope it will. Maybe even more than a couple of years. But this is. I'll show you what the fantasy is. It's this. What you want is you want to take a CVX-like script. Okay, fact number one, you want it to be in a real language like Python or something like that. So let's start with that. So you would take some kind of Python version of CVX. There have been many, actually. So you take one, and you write a tiny little 15-line script, and you run it on your laptop. You like what you see. By the way, if you don't like what you see, there's no point scaling up. So that's simple. That's almost the better outcome, right? Because then you can go camping for the weekend. So, but the idea is, what you really want to do is you want to try it and say, okay, that's promising. That's very interesting. I just tried it with 10 generators, 20 transmission lines, and 20 time steps. Actually, I like what I'm seeing. Then what you want to do is you want to say, okay, now I'm going to run it on a different computation platform, but on a real size problem. So you want to go to EC2, or you take your data, your private data center, and you want to say, now I want to try it with 1 billion examples, some machine learning thing. And you want the same script to run. So, this is the fantasy, right? So you can ask for anything you like, right? So that's the idea. So that's not there. So I'll say a little bit about how do people look at solving absolutely gigantic problems. And this is a very old idea. You just do distributed optimization. And the idea there is you have a bunch of devices or processors or agents. This works at many abstraction levels, right? These could be threads. They could be complete, whole centers that are going to communicate and independently do stuff. They could do all sorts of stuff. But the idea is they're going to coordinate to solve a large problem. And the way it's going to work is you're going to have a bunch of entities. They're each going to solve a problem, a small problem, not a small problem, but a problem. And then they'll exchange messages and coordinate. And then hopefully they'll converge to what would have happened had they solved the whole thing from the beginning. Okay. So, just a baby example. This is not, of course, what it's for, but to give you a rough idea. Suppose you want to minimize something that's a function of two, these could be vectors, but this is a function of the first two variables. That's a function of the second and third, and that's the first and third. And you get a picture like this, right? And so the idea is roughly, by the way, you can interpret this line, well, if you're an electrical engineer, you can think of it as a wire, and it basically says this value of x1 has to equal that value of x1. We'll get to that. So this is sort of the picture behind this. Okay, this is a huge old method. It goes way back. A ton of stuff on this, and I'm not gonna go through this. But I will mention that that my group and a lot of others have been looking at a method that actually goes back to the 80s, in fact, even the 70s, and you could even make a reasonable argument that the ideas go back to the 50s because it has to do with operator splitting and things like that, right? So, and it's called, there's many things. One is called alternating direction method of multipliers, and another name for it is Douglas-Rackford splitting. They're identical. But it actually is very well suited to modern systems and problems. Actually, that's a lie for a reason I'll tell you later, but it sounds good. Yeah, okay, so it may not be a lie for long, but at the moment, technically it's a lie. But okay. So the simplest optimization problem you have, distributed, is this. What you have is you want to solve a problem where you want to minimize a sum of objective terms. Okay, that's it. So, and by the way, if you want to think of this as in a practical way, it's very simple. X is a vector of parameters in a statistical model. Let's say it's weights in a classifier. That's all it is. Just weights in a classifier is a spam filter. Fi is going to be the loss function for the ith block of data. So I have, well, let's make a click-through model. So I want to model whether the probability someone's going to click on something, click through on some ad, right? So I have one web server that does it. I have a whole bunch of them. And each of these has collected, let's say, 1 billion examples each. Okay? So that's the idea. And so you put this in what's called consensus form. Now, consensus form looks like this. You take this problem, and you immediately say, well, everyone can have their own opinion of what x is. So that's, instead of x, it's now x sub I. And then you add the constraint, which is, however, all opinions must be the same. So now this looks kind of silly. This doesn't look like this is going very far. If I walked up to you on the street and said, please help me solve this problem, you'd say, this says that they're all the same, and so that's that. Everybody see what I'm saying? But if you take this and apply this operator splitting or ADMM to this, you get actually a very simple algorithm. It's very, very simple. It says this. It says, in each step, each of these completely independently minimizes its own local objective function, plus, and then a quadratic. And then I won't even go into what the quadratic is, but it's driven by this variable u and the last average. Okay? And then this u is updated as the previous u plus the difference between your private opinion and the last global opinion. By the way, that's an error. This says that u is the running sum of the errors. And if you know about control, this is integral control. So this is 120 years old. I mean, not this exactly, but the idea is 120. This is integral control. So the idea is here, it turns out under very general conditions, you get the global minimum. It's a distributed method. And the coordination is via this averaging. That provides all the coordination. So it's a beautiful statistical interpretation, too, because what it says is that it says that if I have a bunch of entities, each has access to some gigantic pile of data, then it says that all each one has to do is minimize its own local loss plus a quadratic. If its loss is the negative log likelihood function, the quadratic is the negative log density of a Gaussian. So actually what it says is that all I have to do is I have to ask each block to do map, and I pass in the mean of the Gaussian prior, and then they come back. I don't care what method they use. They can use whatever method they like. They just have to do that. And what's interesting about that is by wrapping just very simple stuff around that, we can drive them into consensus, and what will happen is they will have solved the original problem as if they had collected all their data in one place and solved it locally, right? So that's the idea. Okay. Yeah, you wouldn't push this too far because I have colleagues who actually work on privacy-preserving things, and this, I think, doesn't qualify. But it sounds a little bit like it, right? I mean, at least informally, we can say that if I wanted to fit a statistical model to something, and I went to one hospital, and I said, over your 10,000 patients, please fit this model, and I went to another one, then by the time the consensus is done, I have a model. I've actually used everyone's data, but it would be kind of hard to pull out an individual thing. Anyway, but I'm not going to push it because I have colleagues who actually do privacy preserving, and as far as I know, this doesn't qualify. So, okay. So let's look at an example. It's a super baby problem. It's just this. What it is, it's 2 features and 400 examples. By the way, you can solve a problem like that in about 60 microseconds. That's how long it takes to make to classify those things. But we'll split these 400 examples into 20 groups, but we'll do it in an evil way, which is we're going to actually, every group of 20 is either going to be all positive or all negative. So what it says is there's 20 blocks of data, and you get a block of data, and it's like spam, 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 like this, right? So each one, I mean, if that's what you've seen, and I've asked you to make a classifier, very easy, right? If everything you've ever seen is spam, and you're asked to make a classifier, here's the classifier, ready? Return spam. So, I mean, it's not, you know what I'm saying. So the point is, this is a case where they have to talk. They have to consent. They have to go to consensus. If you're not going to get a classifier. Okay. So here's the picture. These are all the independent. These are the 20 independent classifiers. Of course, they're terrible. Well, duh. Each one has seen an extremely skewed view of the world. Either nothing is spam or everything was spam. So of course they're doing terribly, right? Actually, embarrassingly, even you average them once, and it's pretty good. That's the first step. You run ADMM for 5 steps, and this is what's happening, right? So they're pulling together, and there it is after 40 steps, and that's the global classifier. But what's cool about this is to think about it is this: is that basically there were 20 blocks, right, of data. Each one has absolutely no idea how many other blocks there were. No clue. Just nothing. They each support exactly one method, which is that a prior comes in, and they say, well, based on that prior and my data, here's my posterior, or my map. That's all that they do. And they each do that 40 times, and they have come to find a classifier, right, which is actually the same classifier you'd get if you collected all the data in one place and then computed a classifier. So, I mean, it's kind of cool, actually, I think. Yeah. Okay, so just for fun, I mean, you could do this with real-size stuff, too. So here we just made some gigantic, I mean, it's not that big. We could have made it bigger. I think if we went bigger, it would have cost more on EC2 or something like that. So just to prove a point, we just made some problem with some gigantic, dense lasso. And then Neil, a student of mine, wrote a very simple thing. It's just basically it's pedagogical. So the point is it's not supposed to be short code. Very simple, utterly non-optimized. It's in C using MPI and actually the GNU Scientific Library. It's completely untuned. So you could divide these numbers by 10, but that's really not the point. And then it splits into 80 on 80 cores. It's done on 80 cores. And so here's what it takes. So just loading the data is 30 seconds. A factorization that's split into 5,000 by 8,000 matrices, that takes 5 minutes. Oh, by the way, that's how long it would take you to do least squares on this thing if you knew how to do distributed least squares and you did it correctly. So if you got all 80 cores all running flat out, 5 minutes later, they'd be combined and you'd get a solution. That's if you know. Otherwise, it would be 80 times that on a single thing, right? So that's 5 minutes. Then after that, the subsequent ADMM iterations were about a second, right? And then it took only 15 iterations, and so the total time was on the order of like 5 to 6 minutes to solve. Oh, by the way, that's least squares. That's regression. That's completely that's sort of the traditional statistics. And this would be lasso. And the numbers are the same, I mean, for all practical purposes, right? So these are big problems, and you could solve a whole lot bigger ones. And then actually, since then, people have solved way bigger problems than this one on that one. So that's the idea. Okay, so I'm just going to summarize. Actually, the summary is pretty straightforward. It's really simple. It's this. The first is convex optimization. They come up in a whole lot of applications. I mean, that's actually the cool part. Well, that plus the second one. You can actually solve them effectively, right? If they're small, you can solve them at microsecond and millisecond time scales. If they're medium scale problems, it's just like 9, you got a couple of seconds or 10 seconds or a minute, you can solve it on a laptop or something. It's no big deal. And you can solve really big ones using distributed optimization. Now, I should say that some of these are more at the research level. Some of them are much more established. But these are not too far from the truth. This one is relatively far from the truth. When I said that I was lying at one point, what I should say in full disclosure is that in fact on a lot of modern systems, it's just a huge pain to coordinate everything and make it work and all that kind of stuff. But okay. So references, actually this is kind of outmoded because you should just type, if you type any string, anything related to any of these things into Google, you'll find these things. So I think what I'll do is quit here, and I'd be very happy to answer questions about any of this stuff. Yes?
Question.
Oh. Is that a question?
Yeah.
Oh, yeah. What is it?
So just relating to your first part of the talk, so sparsity seems to be the key, right? And you mentioned this example of gene features identification. So I'm wondering, is there a way that you could use all the knowledge that we know some genes are definitely a cause? Can you, how do you, or I guess the question is how can you kind of
How do you put in, so I'll rephrase your question. How might you put in prior knowledge about sparsity and things like that into these things? Actually, there's a very simple way. It's just to weight the sum of the absolute values. Just that simple. If you're pretty sure something's non-zero, put a weight equal to 0 on that absolute value or a small number. If there's a term where you'll pull it in if it's valuable enough, but you really don't want to use it, put a high weight on it. So, yeah.
So,
yes.
So there are a whole bunch of real-world problems which are not convex.
Absolutely. In fact,
network, for example.
Many
more.
Yes.
So you mentioned that there's a biconvex
yes.
in the beginning. Is there any connection between that move, sort of part of theory, into non-convex problem?
Yeah, so it's actually a real, so the question is, the first was an observation that many problems are not convex, which of course is absolutely true. And then the question was, what can you really say about biconvex problems and things like that? It's a great question. One thing to do is to simply do alternating minimization, and then hope nobody asks if you're computing the global solution. I would actually highly recommend that. So if you're in a field and this comes up, you just say that. You say a very traditional method is to alternate, but you should be very careful to never say something like the solution. You obtain an estimate or something, then you're okay. So, seriously, the question is, what does it help you to say it's biconvex, right?
How do you design biconvexity from a fixed non-convex problem? I think that problem is difficult.
Oh, that's pretty straightforward. Yeah. Because once you're biconvex, it's everything, right? So that's NP hard. You name any problem, and I can make it biconvex.
Turn a non-convex problem into potentially biconvex.
There's lots of ways to do that. So I'll be happy to talk to you about it afterwards. But there's a lot you could do that automatically if you wanted. Okay. The real question is, what can you say? What can you really say when you say that problem is biconvex? And if you're under oath or something like that, then you would have to say nothing. Absolutely nothing. Or you could say, my attorney has suggested that I say nothing. That's it. But on the other hand, honestly, that's what normal optimization is, so-called nonlinear programming. So then you might ask, is it better to use the alternating convex minimization or just run a gradient method like we used to? I personally would probably do the convex, but no, I couldn't really stand here and with a straight face say, oh, that's much better than running a gradient method, because it may not be. That's a great question. Yes?
So in the context of ADMM, when you said in the example that you split the data in the evilest possible way,
yes.
I was wondering that for those applications where you actually do have some flexibility in terms of how you partition the data, what is the variability of ADMM in terms of number of iterations before conversion?
That's an excellent question. So the question was, if you're using ADMM to split up a problem, let's say statistical estimation, how should you split it? And what happens to the runtime and stuff like that. So it turns out it's a very complicated question. Because if you split it one way so that one processor got all of one variable or all one features, then they can solve that problem super fast. but you'll have a lot more iterations to converge. Now, the other way, which actually is what people do, I mean, not many, but I know people who have done this, is you actually just hash the data. So what happens is I got 1 billion examples, and I split it into 100, and I give everybody 10 million, and randomly. So what happens there is if I give you 10 million examples, you can probably come up with a pretty good statistical estimate just on your own, right? You know, that might be something that fits in a single machine with a lot of memory or something, and so you solve it there. Then the only thing ADMM is doing is you're gaining statistical power, right? Because I mean, if I send each person, each entity, 10 million entries, 10 million examples, right? And then I say, please send me back your if they send me back statistical estimates and they're all completely different, it's time to go home, right? Because you're not going to get a good classifier, or it's not going to work. So just give up right then and there, right? Well, what will really happen is they'll come back and they'll be a little bit different. I mean, they'll agree on a lot of the features, but you know, on some of the others they won't. Then what you do when you're running ADMM in that situation, all you're doing is you're gaining statistical power. You average them, broadcast, actually you do an all reduce, you know, they get it. And then what will happen is you'll end up with something that is what you would have gotten had you collected it all in one place. And then typically it takes like 10 steps at most, like 5 or 10. So bottom line is I don't think it's really known. And these are the two extremes, right? One is to do full-on partitioning, you know, use some spectral partitioning and make it so that this saw only those variables. At the other extreme, it's like hash it. That's the exact opposite. That's like, and since I can make an argument for either, that suggests, well, I don't know. So, yeah.
So the other alternative would be to do something like stochastic gradient.
Yeah.
So do you have any thoughts on one versus the other?
Yeah, well, I mean, yeah, so the question is, you know, how does that compare to stochastic gradient? No, I mean, so that's what people really use now. They use stochastic gradient, period. That's what's used. But it's a bit weird and unfair even. What happens is, to ask the question is a bit weird, because modern computing platforms are optimized for things like stochastic gradient. Okay, that's when people built the systems and the schedulers and all sorts of other stuff, and the distributed file systems, they had this in mind. So then what happens is if you implement something like this just out of the box on one of these systems, it's terrible. You know, you spend all the time serializing and deserializing data and stuff. It's a disaster, right? So it's actually a harder question. I mean, you should ask the question, how would that compare to something where the schedulers and other things have been set up correctly to handle this kind of thing? And my answer to that would be a resounding, I don't know. I really don't. It's easy to imagine cases where this would be a good thing to do. Right? If you really had different servers that were computing things and did not intend to share their data or something, yeah, this is reasonable, and people do this now. Yeah.
More questions.
So if I have a data set and I know the problem's convex, I can get the solution as you say.
Yeah.
But if I'm doing it in real time.
Yeah, we should be careful. A solution. The solutions do not have to be unique.
Okay.
Yeah.
If I get a solution.
Yeah.
And if I'm doing this in real time,
yes,
and my data is coming in at the rate comparable to how quickly I can compute,
yeah,
can something meaningful be said about optimality versus maybe stability, I guess, for lack of a better word? Can I do something meaningful still?
Yes, people can do, I mean, you can look at algorithms. By the way, the one I showed you would not be a good candidate for that, but you can look at anytime algorithms, which basically says, here's some new data, start computing the answer. But sometime later, I'm going to send you a message that says, time's up, give me the new value. And an anytime algorithm would be one where if you finish and just sitting there and I query you for the solution, back comes the solution. But if I query you early, what comes back is, if not the solution, you're getting there. Yeah. So there are algorithms like that. Actually, just ADMM applied on a small thing will work very well for that. Yeah.
Okay, if there are no more questions, let's thank Stephen again, and feel free to come up front if you have more questions. Thanks.